In question 2, we have a trolley of mass 0.80 kilograms on a horizontal surface attached to two identical stretched springs, each with a spring constant of 30 newtons per meter. They can be assumed to obey Hooke's law and remain in tension as the trolley moves. In A part 1, the trolley is displaced to the left by 60 mm and then released. We need to show that the size of the resultant force at the moment of release is 3.6 newtons. Well, at equilibrium, both springs will exert a force F of equal magnitude and opposite direction on the trolley. When displaced, one spring is extended, exerting a stronger force, the other is relaxed, exerting a smaller force. The resultant force is the vector sum of these changes. For one spring, the change in the force is equal to the spring constant times the change in the length. This is 30 Newton meters times 60 millimeters, giving a change of 1.8 newtons. So the resultant force will equal the force plus the change in force for the extended spring, minus the force minus the change in force for the contracted spring. This comes out at just 2 times the changed force. This is 2 times 1.8 newtons, which is 3.6 newtons as required. In part 2, we need to find the acceleration of the trolley at the moment of release, stating its direction. Well, acceleration is force over mass, which is 3.6 newtons over 0.80 kilograms, giving 4.5 meters per second squared, and this will be to the right as the trolley was displaced to the left. In B part 1, the oscillating trolley performs simple harmonic motion. We need to give two conditions which have to be satisfied to show that a body performs simple harmonic motion. Well, for a body to undergo simple harmonic motion, there must be acceleration always directed towards the equilibrium position, and the magnitude of this acceleration must be directly proportional to the displacement from the equilibrium position. In part 2, we're told the frequency of the oscillation of the trolley is given by this expression, where m is the mass of the trolley and k the spring constant. We need to find the period of oscillation of the trolley, giving an appropriate unit. Well, putting in the values into this expression gives a frequency of 1.38 Hz. Time period is 1 over frequency, which comes out at 0.73 seconds. In part C, we're told copper ions in a crystal lattice vibrate in a similar way due to the interatomic forces. In part 1, we're told the spring constant of these forces is about 200 newtons per meter. The mass of a copper ion, 1 times 10 to the minus 25 kilograms. We need to show that the frequency of their vibration is about 10 to the 13 Hz. While using the same expression, putting in the values relating to the copper ion gives 1.006 times 10 to the 13 Hz, which is around 1 times 10 to the 13 Hz as required. In part 2, if the amplitude of vibration is 10 to the minus 11 meters, we need to estimate a maximum speed. Well, from the formula sheet, the maximum speed is given by 2 pi fa, where a is the amplitude. Putting in the figures gives 630 meters per second. In part 3, we need to estimate the maximum kinetic energy of the copper ion. Well, kinetic energy is mv squared over 2. Putting in the values gives 2.0 times 10 to the minus 20 joules.